After this, it's going to be smooth sailing for the rest of the, I promise, okay? And so let's go ahead and just recall what we've done so far with addition. We've defined addition for a couple of different scenarios, okay? Whenever we have 1 plus x, we've defined that to be x successor. I guess, let me just change this to y, just because it'll appear a little more consistent with our next definition. So this is just the case where we've added 1 plus a number. We define that operation to be the successor of the number, okay? Now we want to know, how do we take the successor to a number and add it to another number? We're not doing successor to a successor here. We're just saying let x be any number. Let's take the successor of that. So the way this is defined is by taking the sum of the two and taking the successor. Okay, and this is something where Landau is not clear at all. And I mentioned how much time I've spent on this proof. That was my main hang-up, is that when he writes that equation, he's defining addition using that property. Okay? So, well, I had to figure out that that's what he was doing, is defining addition in these lines. Because when I was first working through this proof, I thought that this was the definition of addition. But it's not. Those are just properties that addition has to satisfy. The actual definition comes later. And what we're proving right now is we're proving that if you define addition using these two definitions here, that whenever you have 1 plus a number equal to the successor, and whenever you have the successor to a number, where is it? Successor to a number plus a number, you add the two and take the successor of that. We're defining addition using these two equations. And then what we're doing is we're saying, let's verify that the two properties that we want to hold actually hold. So we want to verify, based on those definitions, do these two properties hold? Okay? And what we've done so far is we've verified those two properties, that x plus 1 has to be x successor, and x plus y successor has to equal to x plus y successor. We've verified these two properties in the case that x is equal to 1. And now what we're going to do is we're going to take this definition here. So basically, we've only worked with this one definition so far. This first definition says, let's define addition of 1 plus a number to be the successor of that number. So we've only worked with this one definition so far. And we said, hey, those two properties that we want it to satisfy, that definition satisfies them. Okay? Now we're going to move on to this definition. And it says, if you want to add the successor to a number plus a number, you add the two and then take the successor of that. So that's the second definition. And we need to verify, does this definition satisfy these two properties? Okay? So where we left off on Tuesday is we had two things that we needed to show. Let me find a marker that works. We have two things that we need to show. Is it true for x successor plus 1 that this is equal to yeah, there we go. Is it true that when we have x successor plus 1, that it's equal to this number's successor? Okay? So in other words, whenever you have a number plus 1, is that equal to the successor of this number? So we need to show, need to show that holds, because that's one property that we want our addition to satisfy. That whenever you take x plus 1, you get the successor to x. And we also need to show that this property holds. That whenever you have x successor plus the successor of any other number, that this is equal to x successor plus that number and the successor of that. Because that's what this property says. It says whatever this number is, if you add a successor to that, it has to be the same as adding the numbers and taking the successor. So these are the two properties that we need to satisfy. And whenever we have addition defined in that way, that's what these two properties look like. Okay? Okay, so in class, the video that we did, the lecture that we did, I didn't make a couple of things clear that I wanted to make clear. And so I'm going to do a little extra video to insert into the lecture that'll hopefully clarify a couple of things about the proof of Theorem 4. What I wasn't making clear was a couple of the inductive steps, and so I'd like to make those clear now. So what we've done so far has been pretty simple. We said, okay, we want these two properties to be satisfied. That x plus 1, we want that to be x successor, and x plus y successor, we want that to be x plus y successor. Okay, so we want these two properties to be satisfied, and what we do is we say, okay, define addition in terms of 1 plus y to be y successor, and x successor plus y equal to x plus y successor. So these are the two definitions of addition that we have. Okay, and based on these two definitions, we want to show that these two properties hold. So that's just a recap of where we left off. Now, what we're going to do is we're going to let M be the set of all x natural numbers such that these two properties hold. Okay. So now, I keep saying in class that for all we know, whenever we set up these m's, they might be empty, right? M might be empty. And so our first job is to verify that 1 is in M, which we've done already, right? We've already showed that 1 is in M. So let's just recap the proof here. We want to verify that 1 plus 1 is x successor, right? I'm going to set, then x equal to 1 is an element in M. Okay? To see that, all that we do is we just show that 1 satisfies this equation, right? So 1 plus 1 has to equal whatever this number is, we take the successor to that number, right? So we just get 1 successor. But let's go ahead and recall, right, that we've got 1 plus x equal to 1 plus 1. And let's go ahead and recall that 1 is simply x, right? So this just becomes x successor. And so we get this equation here. It satisfies that requirement that 1 plus x have that reversed. So x plus 1 is equal to the successor of x. So this property, we're done, right? The second property we need to verify is that this holds whenever x is 1. And so what do we get? We get x plus y successor, where y successor is just any arbitrary successor. It's just going to be 1 plus y successor. And then the definition of of addition says take 1 plus any number to be the successor of that number. And then we can rewrite y successor as 1 plus y. That's just the definition of addition. That successor carries over. And that's exactly the property that we wanted, right? X plus y successor. We want it to be x plus y successor. So we've already done those, but it's worth repeating. So what we've done then is we've showed that 1 is an element where these two properties hold, right? Now we want to show that whenever x is an arbitrary element where those properties hold, then the successor to x is another element where these two properties hold. And by induction, that will mean that all natural numbers are inanimate. So what we do, let's let x be an arbitrary element of m. Then we need to show that x successor is also an m. Okay. So to do this, what we do is let's look at that first property. We want to show that x successor plus 1 is equal to x successor successor, right? Because the property that we're trying to satisfy says take any element plus 1, we want to get that thing's successor. And so whenever you have a successor that you're trying to apply that property to, x successor, we're going to take the successor of that, right? It says take the successor of x successor. So what we do is, to see this, we need to define addition. Whenever you have an arbitrary element here, you need to define addition by x successor plus y is given by x plus y successor. So we just define that addition to be anytime you have a successor on the first term, you just add the two and take the successor, right? And so what we'll do is let's apply that definition to this expression. X successor plus 1 can just be rewritten as x plus 1 successor. But the inductive assumption was that x was an element where this property holds. And since x is an element where that property holds, we can rewrite that as x successor successor. And that's exactly what we wanted to verify, that x successor plus 1 can be rewritten as the second successor of x. Okay. So we've verified the first property that says whenever you add 1 in the second place, you need to be able to rewrite that as a successor. And now we want to verify this property that says that x plus y successor is the same as x plus y and the successor of that. But we want to apply that, we want to prove that for a successor to an element where it's satisfied, right? We say let x be something where that property is satisfied. Let's show that it also holds for the successor. Okay? So let me just write all that down. We're going to let x be an m, so we know it satisfies these properties. And we're going to, we need to show that x successor plus another successor can be rewritten with the successor on the outside. Okay. So now what we do is we, again, we have that definition of addition. We just take x successor plus y successor, and we rewrite this successor using the definition of addition that says anytime you have a sum of a successor here plus another number, you can move that successor outside. So that's just by definition. Okay. Now that we're here, the inductive assumption says x is an m, meaning these properties are assumed to hold for x, right? So what we can do is apply that inductive assumption on this inner expression. And so now we've moved that successor outside. From here then what we can do is apply the definition of addition that says if you have a successor outside, you can bring it to the first term. And what is it that we've done then? We've said if it's true that this property applies to x, then it's also true that that property of moving the second successor out also applies when you add x successor to any number. Okay? And so what we've done then is we've done these two things. One is an element of m, meaning when x is 1, it satisfies these two properties, right? And for x in m, we've shown through those last two proofs that the successor to x is also in m, meaning if x satisfies these two properties, then the successor to x also satisfies those properties, right? And so what we see is that by the inductive assumption and by axiom 5, if one satisfies it, and if any element you pick up satisfies it, if the successor to any element that you pick up satisfies it, then m must be all naturals. And so all natural numbers x satisfy those two properties, and those were the two properties we wanted to make sure our definition of addition satisfied. Okay. 1, 2, 3, 4, 5. Okay? And you just continue that pattern. And you now have essentially the natural numbers, right? Yeah. Well, we're going to still use these successors a lot. Yeah, sometimes we'll use these symbols, other times we'll use the successors. Because what do you have to do? You have to go back to the definition of what does 4 really mean. And in the context of this book, it means 1, successor, successor, successor. So whenever we do proofs using these numbers, sometimes we'll use the symbol, but other times we need to break it down to what that symbol actually means. And you may need to write it as 1, successor, successor, successor. Okay? Okay, so here's a good fact to know. This isn't in Landau. This is just any theorem that we talk about today where I don't number it is a theorem that's not in Landau. Okay. So it's a theorem. It's something that you have to prove that 1 plus 1 is 2. Right? We've always just assumed it was true, but actually it's a theorem that you need to prove. I mean, the proof is pretty easy. We start with 1 plus 1. And what's the definition of addition? If you're adding 1 plus a number, you take that number and you take its successor. That's the definition of addition. But what is one successor? That's 2, right? Please don't hate me. I just forced you guys all the way through all that theorem 4. And that's what you get? You get 1 plus 1 equals 2? Yeah, no, I know. Okay, let's take a look at this theorem here. Two plus 2 equals 4. So I'm glad you asked about, I'm glad you asked that question earlier about using these symbols. Oftentimes we are going to resort to writing these symbols using their definition, right? Because at the end of the day, what does this even mean? What does 2 plus 2 even mean? This is a label that represents something else, right? The label 2 represents one successor, right? So what we can do is let's rewrite 2 plus 2 using the sort of proper interpretation. 2 plus 2 is really the same as one successor plus one successor. Everyone agree with that? Okay. Yeah, sorry. Okay. So let's recall the definition of addition. The definition of addition says if you have a successor here that you're adding to another number, what you can do is you can take the successor off of this term and apply it outside of parentheses. Okay? Let me just write up a little chart for us to refer back to, because we're going to use these properties repeatedly. Okay? We have 2 definitions and we have 2 properties. We have that 1 plus x is defined to be x successor. I guess we'll call that lowercase a, okay? And then we have another definition that says, suppose that you have a successor that you add to any number that you want. Then the way that addition is defined is by taking the successor and moving it to the outside of the parentheses. Okay, so it's kind of like you say, hey, I'm going to create a new word. And the word is, let's see, what do you guys want it to be? What's our new word going to be? Spaghetti, that's already defined. So, how about paschetti? Okay, so we invent a new word. It's called paschetti. So you have to say, well, what does paschetti mean? And you just have to give it some meaning. You're making it up, right? So you get to give it whatever meaning you want. And so that's all that we did. We said, hey, look, I'm going to create this new operation. I'm going to call it addition. And then the person says, well, what does addition mean? And you say, it means this. So we just create this property. We say, I want addition to mean this. Okay? So that's what it means to have a definition, is you get to make up whatever interpretation you want for that operation. So we define addition in this way. Whenever you have 1 plus a number, that's the successor. And whenever you have a successor plus any number, that's the same as adding the 2 and taking the successor. Okay? So that's our definition. Now, Theorem 4 was all about proving that it has a couple of key properties. So the first property, and we'll call it A prime. Oh, that's bad, actually, because we have successors. Let's call it alpha, I guess. Okay. The first property says, hey, what if you happen to add those in a different order? Is that also going to equal x successor? And we went through a proof that verified that yes, if you have them in the reverse order, that's still going to give you the successor to x. And beta, this other property that we proved, says, wait a second, what if you have x plus a successor to y? Is that going to equal x plus y successor? And we went through the proof and verified that yes, that definitely holds as well. So we get to use any 4 of these equations anytime that we want. These are true because they're defined to be true, and these are true because we proved them to be true. And so any one of these 4 lines here, you get to use it anytime you're in the mood, okay? And so that's what we did here. We said, okay, all right, I've got a successor here, and anytime I have a successor on that first term, I can just move it outside of parentheses because I defined addition that way, right? So there we used property A. Sorry, this equation here, property A. This equation was true by definition of what 2 means, right? And then this equation here is true by property A. Okay. Now inside here, 1 plus 1 successor, how can we rewrite that? You could use a lot of different properties here to rewrite this. Just shout it out. What do you think? Yeah, it is, but what property? I mean, that is what we're doing, but not property beta. We're going to use property A. So when you have 1 plus any number, that's equivalent to just taking that number's successor. All right, so here we go. We have 1 plus any number, right? And so that's equivalent to taking the successor of that number. Okay. So this thing, by property A, since we're taking 1 plus that thing, we can take the successor of this. So there's the original guy, and then there we've taken the successor of it. Okay? So that successor goes there. Property A gives us that successor, and then that successor was there the whole time.
If we were to translate that into numbers, it would be like 1 plus 2, successor of 3, so that first factor of property A is 4, and then...
Say that again.
So property A would be 1 plus 2, so it's 3, and that successor is 4.
Yes. Yep. Yeah, you've got 1 and then 3 successors, and we defined that to be 4. Yeah. So this first line here, I guess we didn't use property. What did we use? We used property. We actually used property B here. So property B here, and then property A here. Okay? And then this was just the definition of 4. Okay. All right, let's do another theorem. Let's suppose we want to do 2 plus 3. see if I can keep all my different properties straight this time. So let's start with 2 plus 3. Then we know that these symbols have a certain meaning, right? What is 2? One successor, and what is 3? Exactly, okay. And that's just by definition. We defined those symbols to have that meaning. And from here we can start going hog wild. Take any of these properties that you want to use, and you get to use whichever one you're in the mood for, right? So if you have a successor on the first term, you can move it outside parentheses. If you have a successor on the last term, you can move it outside parentheses. Just pick whatever you're in the mood for. I personally am in the mood to move this successor outside of parentheses. Okay, so here we go. Parenthesis, 1 plus 1 successor, and we just moved that guy outside parentheses, and we can do this by, let me get this straight this time, property B. And now, what's on the inside? Two? It's 1 plus 3, but it's 4. It's 1 successor, right? Because what does property A say? Because when you have 1 plus any number, that's the same as just taking the successor. So here we go. We have 1 plus any number. And so by property A, we know that this is take this number and take 1 more successor of it. And the parentheses don't really matter. They're just there for certain steps. On this step, the parentheses don't really have any meaning, so we can get rid of those parentheses. And what do we notice about this symbol here? What does it represent? 5. Yep. So 2 plus 3 equals 5. And have you guys work through that same theorem, but using different steps. Exactly. Because like I said, any of those 4, either the 2 definitions or the 2 properties, you get to use whichever ones you're in the mood for. So, and usually there's lots of different ways of doing it as well. So pick whichever ones you want to use.
Do we have to use the first one by definition?
Nope.
You don't have to?
I mean, you will end up using some of the same properties. Just don't use them in the same order as what we did. Yeah, I mean that first line, you kind of don't have a choice.
Oh.
Yeah, I'm sorry. I'm sorry. Yeah, I mean like where we invoke property A, property B, property alpha. Yeah, the numbers you don't have a choice. 2 is the successor to 1, and 3 is the successor to the successor. So those you don't really have a choice. It's the different properties that you're invoking. Choose different ones of those. Any questions? Okay, so you rewrite them. Well, you want to keep them in the same order that they were. Oh, okay. So you're taking 1 plus 1 plus, 2 plus 2 plus 1. So you're basically peeling this off. That actually is legitimate because you can rewrite 3. Let me show you what I mean. Let me start this way. 1 successor plus 1 successor successor. That's what we're looking at, right? Now, but yeah. But what we're going to do is this 1 successor successor, you can apply property. I guess we're looking at either property. Yeah, we're looking at property alpha in reverse.
Okay.
So property alpha says that if you have a successor, you can write it as x plus 1. And here we have a successor, don't we? Right? We have this thing here, successor. So what property alpha says is that anytime you have a successor, you can write it as this thing, and then that successor can be written as a plus 1.
Is that what I had?
Yeah, I'm just telling you why that makes sense, why you're allowed to do that.
But that's here, right?
Mm-hmm.
Okay. So, yeah.
Good, I like that. Interesting modified version of this proof, okay? So we all agreed that the first line is determined. You can't do it any other way. You have to write 2 using its definition and write 3 using its definition. And so, sorry for the confusion there, but yeah, you have to start here. But then from here, you can do all kinds of crazy stuff, right? And so my favorite proof, actually, Kathleen's proof, she said, look at this 1 successor successor. I'm going to rewrite that using, in this case, we used property alpha. Is that right? And what property alpha says is that if you have a successor, so we're kind of using it in reverse, if you have a successor, you can write it as the number plus 1, right? And here we have a successor, right? Let's write it as this number successor. Everyone see that? So by property beta, you can rewrite this thing as whatever this number is plus 1. Okay, so this equation is true by property beta. Where we're sort of applying it in reverse. It says if you have a successor, you can peel off a plus 1. Now that we're here, where did you go from here? Okay. I wasn't able to follow that last part. Oh, I see. Oh, that just gives us this back, though. Okay. Yeah, so we kind of went, yeah. So that's definitely a different proof. But it's just because we did more steps. So instead of, so going from here to here, you're basically just undoing that step when you go from here to here. So let's go ahead and move in a different direction. And why don't we just peel off this successor and move it outside of these 2 terms. Okay? And then if we have something plus 1, that's the same thing as taking a successor. So we'll group this thing onto here using the successor. And then this 1 plus 1 successor, you can rewrite that as 1 successor successor. Sorry, 1 successor successor. And then we have these 2 successors as well for a total of 4 successors, which is the symbol 5.
I don't understand why we had to take all the steps on the image to just be one successor, and after that, successor, and then successor 5.
Which step here?
It's all of them in the first one until we get to like the bottom third, you know?
Wasn't it just in the
You already know that.
second one down from the top? Would be, or go like in the top, from top of the-
Oh, so okay,
Fourth one down?
this one
Why
here.
couldn't we just move all of them out?
Move all the,
Because there's successor out.
move this one out here.
Yeah.
Okay.
Instead of one, so it's-
Well, we can certainly do that, and that's what I was saying is there's lots and lots of different ways to apply these, and that's all I was saying. So yeah, if you want to do that, you're welcome to, right? You can move this thing out using property, what is that? Property beta, right? And then this thing 1 plus 1 is the same as 1 successor. That's true by property A. And then plus 1 is another successor by property alpha, right? So yeah, and that gives us 4 successors, just like we needed, which is 5. So that's sort of the point. I just do it to show where these pieces came from, right? So this piece here, this plus 1 says take a successor of that. So I'm saying whatever that piece is, put it in parentheses, and we're taking a successor of that. So the parentheses are optional, and it's just there to show you which pieces went where. Yeah. Okay, so yeah, lots and lots of different proofs. Here we proved it one way in class, and then we had one student do this, and then another student, and she actually sort of made a little loop and went back using what we did in class, and then we did this together where we took a different approach, and then another person branched off of here and said, let's take a different approach. So that's my point. Just any combination of these 4 properties, as long as it makes sense, as long as you're following that property to the T and not skipping any steps or anything like that, you'll get a perfectly valid proof. Okay? So, let me see, what other calculations do I have? Why don't you guys prove 3 plus 6 equals 9? 3 plus 6 equals 9. I guess it's not an example, it's a theorem. We're proving this thing. And it's very, very good practice to get in the habit of labeling every equation that you use, because that forces you to recognize whether or not you're properly using these properties, right? So in this proof here, how did we know we could do this? This was by definition of what those symbols meant. To get from this line, all we did was just rearrange parentheses. Right, we took this and rewrote it using some parentheses. And then here, to get this, we used property beta to peel off a plus 1. Right, property beta says if you have a successor, you can write it as whatever plus 1. And then to get from this line down to this line, we took this successor and put it outside. That was by definition of addition, which is property B. And so if you can go through your proof, property B, if you can go through your proof and label every single equation using one of those properties, then your proof is guaranteed to be correct. Okay? So as long as you're using the properties correct, then your proof is correct. Yeah.
So if you have a successor, you have to break down each one of the successors and if not, you can't just be like one successor. And then
Correct,
leave
yeah,
the
because
other one out as,
yeah,
that's
because
basically what it is.
Well, but you have to use those properties, right? That's what makes it a proof, is that you have to use the properties that have been proven. And so we don't have a property that says, well, I'm just going to group these things together.
But they're already grouped together.
I'm talking about these here. I'm just going to take these and just group them together with these. We don't really have a property that tells us we can do that. The only rules that we have,
We can't do this. And, right? And then these. Yeah.
yeah, we don't have a rule that says that. Tell me where in those 4 properties you see that rule.
Where the Y is actually figured out would be it.
Nope. And so you have to combine all those rules together. And that's ultimately what you want to do. But to get there, you have to include all these in-between steps. And every one of those in-between steps has to use one of those 4 properties.
So you could just use the same one over and over and over again.
You can, but you're going to get to a point where you, until you get to a point where you can't. And so what you want to do is fine. You want to cut out a whole bunch of those repeated steps, right? So guess what? You have 5 successors here, right? So all you have to do, you apply this property 5 times, and you just say apply property beta 5 times. You don't have to write out every single step, but you have to make clear that you're using that step and you're doing it repeatedly. But it's not. It's not. That's only one step, is moving all those successors out. Once you get done with that, you're still going to have a sum inside. That sum you then have to modify using one of these 2 rules. Okay? The motive is to get 1 with 8 successors. That's your end goal, is to get 1 with 8 successors. But the in-between, starting at 1 successor, plus 1 successor, starting from that starting point, you want to use the 4 rules to move those successors around to where you end up with 1 with 8 successors.
Yeah.
That's
So when I got multiple successors, like I got 5 here. So how do you break it down? How do you do it? How do I break it down to the total of it? You only have 5 successors. So I'm looking at property B.
which is a good one to look at.
Okay. Because here you broke it down 1 successor, so that's 2 successors. So if I'm trying to do this, would I do 1 successor, or 1 parentheses, 1 parentheses?
Yeah, the parentheses are optional.
Okay, and then like that.
You can put as many parentheses in there as you want. So you could put parentheses just there and just there, or you could put them in between each one, or you could just not put any parentheses at all.
But this is correct.
That's certainly correct. Another way to write these would be if you want a parenthesis here and a parenthesis here. That way you've got one little successor that you can peel off.
And so that
So what I wanted to do is I wanted to go over an example that illustrates that we get to build on this, right? So once you prove that 1 plus 1 is 2, you no longer need to reprove it, right? And you can use that in other facts. Or once you prove that 3 plus 6 is 9, you don't need to reprove it, you can use it in other facts, right? So once you prove an addition fact, you get to use it when needed. Well, we'll do an example so you can, yeah, sort of. You don't have to go through quite as many tedious steps. So let's take a look at an example. Suppose 5 plus 6 is known to be 11. Let's use that to prove that 5 plus 7 is equal to 12. So here's the benefit. So once you prove something, it makes writing things a lot easier. 5 plus 7, let's go ahead and just write that as 5 plus 6 successor. Then property beta says that anytime we have a successor on the second term, we can move it outside of parentheses, 5 plus 6, and take the successor of that. And 5 plus 6 we know is 11, and the successor to 11 is 12. So does that answer your question about pick it up and keep going? Okay. So that's, you have to prove a bunch of these using the successor notation, but once you prove one, then you get to use that in proving others. So now we know 5 plus 6 is 11, and we know 5 plus 7 is 12. Let's suppose that 8 plus 10 is 18. Let's use that to prove that 8 plus 11. Let's use 9 plus 10 is 19. Okay, so 9 plus 10, we'll start there. And we basically just have to back up until we reach a known addition fact. We're assuming that we've proved this already, so we have to back up until we reach that proven addition fact. So let's back that 9 up. Sorry. I'm sorry. I'm sorry. Sorry for the pop culture reference, but yeah. I was like, oh no, it's coming. Don't say it. Don't say it. Okay. So we've reached that known addition fact, right? Because property B says if you have a successor on the first term, you can move it outside of parentheses, right? And so we sort of work backwards until we find a known addition fact that we can use. 8 plus 10 is known to be 18. And we're taking the successor to that, which is 19. Okay, so suppose that, like in these, it was kind of easy because the problems that we had were one higher than one of the numbers. 5 plus 6 equals 11, so 5 plus 7 equals 12. What happens if one of these terms is not just one higher? What if it's a couple higher, right? So suppose it's known that, let's do 7 plus 12 is 19. Why don't we use this to prove that, let's do 10 plus 12 is equal to 22. And so what do? We can rewrite 10 in terms of 7 successor, right? 10 is really the same as, sorry, 7, successor, successor, successor. Right, that says 7, 8, 9, 10. And then we have this property B that says addition for successors is defined where you just take those successors and move them outside of parentheses. And we're able to work backwards until we found a addition fact that we know the answer to. 7 plus 12 equals 19. And then all we have to do is just start applying successors. 19, 20, 21, 22. Anyone feel a little better? Okay. No? 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 Yeah. Yep. Yeah. It's, I knew that. Do you remember that graph that I drew on the very first day where I said it's going to start out being kind of silly where we're like talking about equals, x equals y if x and y are the same thing? Everyone's like, yeah, well, I know that already. And then it quickly shot up in difficulty where it's like, oh my God, I hate you, I want to die. And now it's like, Okay, so we're on that downward slope. Now, unfortunately, it's not all going to be quite this easy from here on out, but it's not going to get like this. I promise, okay?
So will we ever have to revisit that land?
No. No, I'm not gonna force you to, yeah. So, now that we've defined addition and we know how to use addition, we need to know what are its properties. And that's all that Theorem 4 was. It said we're going to define it and we're going to prove that it has these two very basic properties here. But we don't know anything about it. Can you switch the order? Can you rearrange parentheses? How does addition behave with ordering? Right? If you add the same number to two different numbers, do you maintain the same ordering? Something like if 5 is less than 7, and if you add 3 to both sides, does 8 then have to be less than 11? So we've only introduced the definition. Now we have to answer all these basic questions about what properties does addition have, right? And that's all that theorems are. Think of theorems as two things. A theorem is a tool, and a theorem is a description. Okay? So Theorem 5 guarantees that the associative law holds. How do I set it up here? X plus y plus z equals x plus y plus z. Okay? So you can think of this, like I said, in two ways. It's a description of how natural numbers behave, but it's also a tool. It's a tool that says you can add these in any pairing that you want. If you want to add x and y first, that's fine. Or if you want to add y plus z first, that's fine. Okay? Okay, so in the last proof of Theorem 4 that we talked about at the first part of class today, I kind of butchered that. Sorry about that. And we were using induction, and I forgot to mention that. But let's be real clear about it this time. Let M be the set of all numbers z for which the associative law holds regardless of x and y. So we're going to do induction. and we say, let's look at a number z where we know the associative law holds regardless of what x and y are. And you guys are hopefully asking in your head, how do we know that we can do that? How do we know that there are any numbers where the associative law holds? Is that what you guys are asking? You are now? Okay, and the answer is we have to prove that, right? We have to show that there is such a number, but we'll start easy. We'll start by setting z equal to 1. So we're going to show it holds for 1. So let's consider this left-hand side, x plus y, in parentheses, plus 1. And going back to that earlier board that I just now erased, if you have a plus 1 at the end, then property alpha says that's really the same thing as just taking the successor of this number. So this is property alpha from before. And now we have x plus y successor. One of our properties says that we can bring that successor into y. This is true by property beta on that previous board. But what is y successor? It's just y plus 1, and this is true by property alpha again. It says if you have a 1 at the end, that's the same thing as taking a successor. And so what have we done? We were able to pick up these parentheses and shuffle them around to where now they're grouping the second two terms. And we notice we got equals all the way. So the associative law holds in the case that z is equal to 1. Okay? So induction says, let n be the set of numbers where that's true. You have to show that it holds for 1, and then you have to show that it holds for all successors, right? So now what we're going to do, let z be any number for which x plus y plus z is equal to x plus y plus z. So let z be any number where the associative law holds. And now let's consider the successor. So in this expression, we're going to replace the number z with the successor to z. And we notice that in this expression, we have the successor that happens to be on this last term here, the z, right? Property beta from that list of properties says if that last term has a successor, then you can move it outside of parentheses. So this is just true by property beta. If your last term has the successor, you can move it outside of parentheses. Inside these parentheses, take a look. We've got a set of numbers where we just have x plus y plus z. And z, it was assumed to have the property that the associative law holds. Right? That was the definition of M. It said assume that Z is such that the associative law holds. So inside here, all we have to do is just rewrite that using the associative law. This is true by the inductive assumption here. That says assume that you picked up a number where the associative law holds. And now we have a successor on the outside of the parentheses. We can bring it to this inner set of parentheses. This is true by property beta. It says you have a successor outside, you can bring it to that second term. And then we just apply property beta again that says take that successor and move it inside of those parentheses. And what do we have? We have that this set of parentheses, you can pick them up and shuffle those parentheses around to where you're now grouping the second set of terms. We proved that that property holds for 1, and we proved that it holds for all successors. And so by induction, it has to hold for all natural numbers. Yep, yep. Exactly, yep. Exactly, and you'll notice that we do a little of both, right? Here, we're taking the successor, we're moving it out of parentheses, but other times we take that successor, we moved it in once, we moved it in again. So sometimes you'll move them out of parentheses, other times you'll move them back in. And so that's what's cool about those properties is that you can use either direction, right? And that's what you were doing in that one proof that we mentioned on the board is you said, I have X successor. I can peel off a 1 here. If I have a successor on the outside, I can peel off a 1 as a +1, right? Normally, we like to think of this rule as saying if you have a +1, you can write it as a successor, and you used it going the other way. If you have a successor, you can write it as a +1. So yeah, all those rules that we have, they're all reversible. And so you get to apply them in any order that you want. Okay? So there you go. The associative law holds for naturals. That was theorem 5. Okay, theorem 6. The commutative law, which says that you can switch the order of addition. Commutative law holds. I'll just make sure I picked the right number here. Yeah, okay. So again, we're going to proceed with induction. We're going to let M be the set of numbers for which, be the set of X for which X plus Y is equal to Y plus X, regardless of what Y value you picked. I'm repeating myself here, but I'm doing it intentionally. For all we know, M could be empty. Maybe there's no numbers where this holds, right? So one of our main jobs is to show there's at least one thing where the property holds, What is it? 1, right? There is going to be at least one thing where that property holds. And let's take a look. We're going to let x be 1. We get 1 plus y. What's that equal to? Y successor. Yep. Okay, this is the definition of addition with 1. 1 plus anything is that number's successor. That's the definition of addition. In that list, it was property A. But by property B, if you have a successor, you can peel it off as a plus 1. Or sorry, not property B, property alpha. Okay, so in that list, this is true by property A. And in that list, this is true by property alpha. So what have we done? No matter what y value you have, if you add 1 plus y, that's the same thing as taking y plus 1. See how I'm writing pretty much every equation here, I'm writing something about why we know it's true, right? This is true by the inductive assumption. This is true by property beta. This is true by property beta. So it's a really good habit to get into. Write the property that you're using when you use it. Property A says that if you have 1 plus a number, that's the same as taking the successor to the number. Property alpha said that if you have y plus 1, that's the same thing as taking y successor. So each of those equations is justified. And therefore we have 1 plus y has to be the same as y plus 1. So we know m has 1 in there. And now if we can show that the successors to all numbers in m are in there, then we'll have verified that it holds for all naturals. Okay? So let's let x be any number of m. What does that mean? To say that x is in M. It is a natural, yes. What property does it have? Okay, we keep talking about this. This discussion keeps coming up. Remember, you have to be very, very clear about the definition of M. Right, here it is. M is a set of x for which that property holds. So here we selected a number out of M. What can we say must be true about that number? It must be true that you can switch the order. With any other number y, you can switch the order of addition, as long as you picked up that number from M. Okay? All right. For that number, we want to verify that the commutative law also holds for its successor. Okay? So what are we looking at? We're doing the x first. So what do? We just take the successor and add y to it. And property B in that list says we can take that successor and move it outside of parentheses. So this equation here is true by property B. Now, what's true about x plus y? You can switch the order, because we picked up x to be one of the numbers in M. If x is an element of M, that says you can switch the order, right? That's the very definition of what M was. Since we picked this up from M, we can switch the order. So this equation is true by the inductive assumption. The inductive assumption just says, pick a number where you know that condition holds. And that's exactly what we did. We said, let that condition hold. And that's called the inductive assumption. And now we have this parenthesis term with the successor outside, so where should we move that successor? On the x, right? Because that's exactly what we want. We want, if we have x successor first, or if we have x successor second, we want to get the same answer. And so we know. I wouldn't call it the distributive law, no. Yeah. So this is true by which of those four properties? Yep, property beta. Property beta said if you have a successor on the outside, you can apply it to the second term in the sum. Okay? And so what have we done? We know that 1 is a number where you can switch the order. And we know that pick up any number where that's true, and the successor is going to be a number where you can switch the order. So since you can switch the order with 1, that says you can also switch the order with 2. That says you can also switch the order with 3, and 4, and 5. And so M then consists of all naturals. Okay? So this is theorem number, theorem 7. Y is not equal to x plus y. So, any guesses on the technique that we're going to use? Induction. So, what do? We verify that it holds true for 1, and then after we've done that, we verify that it holds true for all successors. And if it's true for 1, and it's true for all successors, then it has to be true for all naturals. So, we're going to let M be all y such that the property holds. Y is not the same as x plus y. Repeating myself for the millionth time. For all we know, M could be empty. Maybe it's the case that that these things are always equal. And it turns out that no. We can show that 1 is in M. So to see that, we're going to take 1 and plug it into this expression where we see a y. What is x plus 1? One successor. And how do we know that? Not one successor, x successor. How do we know that? Property. Starts with an A. Yeah. Okay. And so we have an axiom that says that nothing ever succeeds to 1, right? And it's okay if you don't remember the exact axiom, but does anyone happen to remember which axiom says you can't succeed to 1? Axiom 3. Okay? And now we're going to let y be any number in M. Let's consider its successor, x plus y successor. this is equal to x plus y successor. And this is not equal to y successor. Right, because we said let y be anything in M. What that means is that when you add it with x, it's not going to give you y back. So what that tells you is that here you with x, therefore guaranteed that that's not y, right? No, yeah, we dropped that. Now we're just letting y be any number where the condition holds. Okay? Where the condition is that when you add it with any number, you don't get y back. Okay? So the inductive assumption said pick a y where that condition is true, that when you add y with x, you don't get y. Here we've added y with x. Therefore, it's not the same thing as y. Okay? And the successor doesn't change anything there. And so what does that tell us? It tells us that... sorry. What does it tell us? I mean, we're done basically, but I'm just trying to tie up the conclusion. Yeah, I mean, basically, right? We're y successor plus a number never gives you the same thing back, right? So it satisfies the condition that we wanted, and so yeah. Okay. So 1 is in M, and all successors to things in M are also in M. So we knock out all natural numbers that way. So sorry to go over, but the